Okay, let's speed up for a little bit and finish this chapter. For WLAN, so WLAN is not the key point. Oh, sorry, made it wrong. Sorry, could you still see my screen share? Yeah. Hello? Okay, sorry, I made the wrong action. So here for the Wi-Fi, WLAN is not the key knowledge for H3C&E, but the concept we just need to understand. WLAN is a special kind of LAN because the media WLAN use is the radio. It's the radio. It's not the actual physical cable. It's not fiber, not cable, but it's a wireless radio. Right? Frequency radio, RF transmission. So that's the WLAN overview. And protocol family. So this family is of earlier age. We just need to know the correct name. We know the name is enough, right? Dot 11, 11B, A, G, N. So we just know the name. All the name is okay, right? We don't have to remember all the details. And we can also skip this frequency map. No exam will test this. But for this picture, on this picture, the information is key information because for WLAN protocol, the standard divided the frequency that the Wi-Fi using into different frequency channels, right? Different frequency channel. So these channels, the channels map is like this. But the key point is not to remember the frequency range, the range of frequency, but the key point is to know how to deploy a cellular communication system. So when you design a network, you make sure the neighboring area using the frequency that neighboring area is using do not overlap with each other. This is the key point we need to remember. So which sequence range you choose will not overlap. Back to this map or this channels image, right? For example, 1.6.11 is totally not not overlap. 2.7.12, 3.8.13, and so on. So you could choose to use this this frequency. For example, on this map is a 1.6.11, right? So when you deploy your network, when you design a network between the neighboring area, you could use a 1.6.11 or 2.7.12. Okay, as long as they not overlap, right? So if you are using 1.6.10, if you're using 1.6.10, that means their frequencies overlap and they're going to be interference, right? But just remember, if you choose to design a network, just choose from this pair, right? 1.6.11 to 7.12, right? This is the key point of this picture. And also we need to know, as long as there are no overlapping, your frequency could be used repeatedly. For example, 1, 1, 1, or 1, but they are not overlapping between neighbors, between neighboring area. So this is the key point to design a WLAN network, right? Then we come to the CSMA-CA knowledge. So this is the method that WLAN used to avoid collision. So the difference is the last two initials. It's called CA, not CD. So it's called collision avoidance. So we can know the difference literally, right? Because this mechanism or this method is not to deal with the detection after deal with the collision after detecting it, but to avoid the collision before it happens. The method is, for example, all the stations we could see this as the host, on the CSMA CD picture is all the host. And for the WLAN system, for example, station A already exchanged the frame. They also already sent a frame, and with certain DIFS is a fixed waiting time, and after the fixed waiting time, we could see this line or this WLAN area is idle at this moment. But without sending the frame immediately, the next move for all the station or all the host is to get into a backoff time randomly immediately. They do not send the information. They don't send the information or send the data immediately when detect the idle. They detect the idle and they back off immediately with random backoff time. And the station with the shortest backoff time, for example, this station 3 is only 3 seconds. For example, the second, if the unit is 3 seconds, then this station will send the information or send the frame most quickly or most fast, right? Most early, and so on, and keep doing this. Sending the information, idle, waiting, sending. So the difference with CA and CD is CD will send the information immediately when detect no carrier. But for CA, the frame will not be sent immediately when detect idle. They back off at first. Right, this is the difference between CA and CD. And for double line application, there are two kinds of ways or two kinds of a double line application. The first one is hotspot. Hotspot is using in this kind of topology, right? This is the core network. This is the AC. This is the AP. This is the access point of the Wi-Fi network. This is a radio. This is a radio, and connection is to client. So this kind of design is a hotspot design. On the contrary, another kind of design is called wireless bridge. You can see the radio is between the wireless bridges, right? So this kind is a wireless bridges connection. So these two definition is based on the different design of use of the AP, right? Okay, as a summary, we give a very quick look of this LAN technology. So we know that LAN technology exists in layer 1 and layer 2, right? And we already know several key information. For example, what is hub, what is switch, and which layer they works at, and how to distinguish collision domain, and what is CSMA, CA, and CD. So what is WLAN? This is the key point of this chapter's learning, right? So by now we have finished 3 chapters, and let's take a rest for about 5 minutes, and after coming back we start the chapter 4 and chapter 5.
哎，南哥啊，
哎，
你今天要讲就是那个 PPT 1到几啊
1到10，
？1到10讲完是吧？Yeah，
对，
1 to 10，因为小一不在问，
因为没这么
现在
讲过，
讲几个？
所以讲了3个，
还有7个，有点挑战呀。
是不是？是因为这样的，因为
啊，
4、5章就是前5章到第6章，我一定要给它讲的很细，第4章我不会讲的很细，
好的，
因为以前这些我是要
好的
一天讲完的，变成半天讲完了。
，OK，
嗯，后面呢
好的，
我会把不重要过掉。
好，
Okay, let's. Oh, sorry. This one. Yeah, okay. So let's move on to the next chapter. So WAN fundamentals. For WAN fundamental, WAN information is not the key chapter for our SJCNE. So we just point the key point that you need to pay attention to. So to make you more smooth in your exam, right? So compare with the LAN when came out into use or came out into developed just because just to solve the problem of the transmission distance, right? Because so many kind of LANs they can only transmit with a very short distance limitation. But in order to transmission between cities, transmission between province, um, developers make a new concept of make a concept of a LAN of a WAN come out. So the transmission distance is much is measured by kilometers, so compared with LAN. So this is why WAN come into develop. So for WAN, so this is also the same constructor or same layer with LAN, right? Just a different protocol, you could see. Also layer 2, layer 1, different protocol. The information we need to remember is HDLC PPP, frame relay is the common use protocol. And for the physical layer, the cable, we remember V.24, V.35. This is okay. Other name, if we find this name, we know this is a WAN cable. It's okay. It's not a LAN cable, right? For detailed information, just we know v.24 and v.35. And type of WAN connection, just remember these three types. And circuit switching and packet switching we also mentioned just now. The feature circuit switching is quick, but circuit switching is quick, but with circuit switching compared with packet switching is much more quick with no latency, involve no latency. But the problem is it's very long time to build a connection. Right? The packet switching is more involved latency, but the reliability is higher than circuit switch. So this feature will show up in your exam, but you need to pay attention. And about the lease line, circuit switching connection and the interface and the cable, this we can just take a reference or take a look. We don't have to remember all the information. But for v.25 cable, this is the typical cable for WAN. So the key point is this page, the information on this page is very important, right? We need to remember what kind of mode it supports. It supports synchronous mode or asynchronous mode, different transmission mode. And what is the speed? What is the maximum speed? Oh, sorry, maximum rate or maximum bandwidth it support under different mode. So why I say this is important, because when doing the exam, they will show you some circumstance that customer want some kind of speed or some kind of bandwidth, and they let you to have the cable to choose which cable you could use, right? So when this question happens, you need to remember the bandwidth, exact bandwidth and exact mode to make the answer, right? And also for v.35, remember, is only support for a synchronous mode, but the maximum rate is the 2 megabps. For WAN cable, 2 megabps is the already very fast speed, very fast bandwidth, right? So comparatively, we remember, repeated, v.24 both mode, but the speed is low, right? The speed we need to remember. But for v.35, synchronous mode only, but the speed is 2 mega. Right? And other cables, we just have a reference. Okay, so this is for WAN chapter, right? We just remember the key points and remember the knowledge point, right? So then we go to another important chapter we're gonna take time is IP fundamental. For IP fundamental, we could see that our knowledge already move up from layer 1 to layer 3. IP fundamental is a network layer in OSI model, right? So in this chapter, we're going to know some basic knowledge of this protocol. This is firstly, again, back to the OSI model, is a network layer protocol. And about the 3 questions, what, why, and how. So we overview of the IP, we will take a look at what is this protocol, right? What is the network protocol is. So overview of IP is, we could see this protocol tree or protocol map. You can see based on different layer, So IP protocol exists in network layer, right? In this layer, we have actually 5 protocols to remember. IP protocol it is, and ICMP, IGMP, ARP, RARP, right? They all have their functions. And down this layer, there's a data link, Ethernet token ring. Up this layer is a TCP and UDP. And besides, we need to remember the protocol number 6 and 17. This is the exam point, right? Based on IP network, IP layer, there's a TCP UDP layer with different protocol number. In other words, for IP protocol, is use protocol number to distinguish, to tell the difference between upper layer protocol, between transport layer protocol, right? This is the structure. And what is IP? IP's function already mentioned in the LAN fundamental, in the OSI model, because IP protocol is network layer protocol. So the basic function, the main important function is firstly to assign the IP address, to identify every node in the IP network, in the logical IP network. So the function number one, identify everyone, right? Give them the unique IP address. And addressing and forwarding, right? To find the path and do the layer 3 forwarding, do the network logical forwarding. Right. This is the main function of IP. Main function of IP. For this, adapting to various data link, that means no matter what kind of layer 2 network it is, they can all use IP. Right. This is the third sentence meaning. So this is the meaning of the third sentence. Right. IP support for abundant types of layer 2 protocol. This is the main function of IP. So that what IP. So the structure, what IP structure is, you can see on this map. 5 hosts through 3 networks. Network A, 4 network, 5 hosts. Network A, B, C, D. Right. So the IP network structure divided the host or the devices into different IP network segment, right? Separate the segment and forward packet between the segment. So this is the IP's network doing, right? Separate the hosts into different IP network segment. And here, the next step is about the header. Any question? Let me check. Okay, about the notes, we may do this at the last day. We will have a review. Okay, so format of IP header. We just imagine back to the OSI model. We see the picture that when doing the communication, we have the header encapsulation and header de-encapsulation, right? So this header is a layer 3 header. It's called IP header because we're using IP protocol, right? So on this header, we could see so many fields, and the key information is, remember, the IP header is no less than 20 bytes. Sorry, right? The IP header is no less than 20 bytes because of if there's no options and paddings, it's 20 bytes at least. If some IP header is lower, is less than 20 bytes, the system will recognize this IP header as a wrong packet. This is the key information, 20 bytes. And the meaning is the several meanings. You could also refer to your context book, but the key fields is version. IPv4, IP protocol has 2 versions, IPv4 and IPv6. So this version is because it's a 4-bit, right? 4-bit is a represent for the version number, right? So time to live, also the important fields, right? This represents the how long or how many hops this packet could still survive or still live in the layer 3 network. So if the packet is forwarded by a router or by a layer 3 device, so the time to live TTL will drop by 1, and the maximum number is 255. So if this field drop to 0, the IP packet will be dropped by the next hop. So this is what time to live is. Protocol number, right? TCP UDP protocol number, and important one, source address and destination address. So because we already know IP protocol is to identify everyone with the IP address and to find the path, find the routing, find the routes, right? So the route is to find the correct destination address, IP address. So they also exist in a pair, source and destination, right? This is the key fields of in an IP header. But for the other fields, if you want to know the meaning, you could refer to your textbook, right? Okay. The next move we'll get to know the IP address format and representations. So already mentioned, right? A IP address can be divided into network number or network address and a host address. Right? This sentence is important. Please remember, a IP address divided into network address and host address also could be called network number or host number. And the total length for IP address is 32 bits, binary numbers. And the formal pattern is dotted decimal. The transform is doing is like this, right? Everyone is a 32 bits address to be divided into 4 8 bits, and to use one decimal figure to replace the binary figure, we got a dotted decimal pattern of IP address. So this is the concept of IP address, the pattern, right? About a network number and host number, we could take a look at this picture. There's a router in the middle and two interface, right? Two interface, and on different interface we could configure different address. And this router divided in the network into two IP subnet. One is this 192, 168, and .2 network, right? By interface 0/0. Another one is a 10.0.0.0 network is by port 0/1. So we could see this network, this subnet, the network address is 10.0.0.0.0. So the network network address represent this whole network share the same network number is 10, right? For this interface 0/0 is represent a network with a network address is a 2.0. So all the network, all the hosts, right, hold the same network number with this number. So we could see different network have a different length of a host number, a network number, and also the different length of a host number, right? So the shorter the host number is, the numbers of a host that this network could accommodate is less, right? The longer the host number is, the PC or the host that the network could have or could accommodate is more, right? For example, this network 10 network 10 could accommodate maybe hundreds of hosts, or hundreds of hosts. But for this network, maybe just a 255 hosts at most. Maybe this is hundreds of thousands of hosts. Right? This is the difference. And upon already know the network address and the host address, so we should get familiar with the class that defined by the protocol, and also this class is being used on the public network, aka internet. They accord or comply with these rules, with this IP. When they choose the IP address on internet, they're according with these rules, right? We'll take a look. For class A, it's with 8 bit of network address and with 24 bits of host address. So this kind of network address, this kind of address could accommodate a lot of hosts compared with others, right? I said just now, with longer host bits it is, so the host can accommodate a little bit more, right? This is class A. For class B, it's a 1616, a 16 bit each. And for class C, it's a 21-bit network address and host is 8-bit, right? This three from A to C is being used on internet, right? So the most additional information is the most class A address on internet is has been assigned to the superpower countries such as America, United States, and other allied countries. So they are using this class A network. So these countries are the pioneers in building the internet. So they're first there, earlier there, so they got a good class of IP address earlier, right? For the followers, maybe they only got the class B and the class C, right? For class D is reserved for multicast address, right? These are not used to design the public address, and class E is reserved, not being used. So this is the classification for the former IP addresses, right, in public network. And there are also some special addresses with different, with the usually full 0 and full 1 for network number or host number. And so talking about some special about the host number, for example, if it's all zero on the host number, but the network number is any, it's not 0, but the host number is all 0, that is a network address. It's called a network address. It's identified as a specific network segment, right? For example, the 10.0.0.0, the network address, because it's the host number of the address is all 0, so it's a network address. It's not represented for a specific host, but a specific network segment, right? But if the host number is the full 1, that is the broadcast address of this network segment, right? And if the address starts with 127, it's a loopback address for testing. It's not using for building network, right? All 0, that means all network. It's logically all network. And all 1 means broadcast address of all network. So this is the special IP address rules, right? And also there are other two kind of a protocol that exist in IP layer, in network layer. So it's ARP and RARP. So what is ARP? We take a look at this picture, we get a basic idea. So let me say there's a host want to communicate. We want to communicate with actually 1113. Why? Firstly, we want to understand the circumstance. We need to back to the OSI model, right? We just recall a host want to send out something. They will encapsulate the packet, encapsulate the information from top to layer by layer, right? We just say the host A is encapsulate the information from application layer, transport layer, and then to IP layer. And to IP layer, if the information destination IP address in the header pointed to 1113. That means the application layer want to find 1113 and communicate with her, right? So, but when by layer 3, the information is enough, right? Because the network layer know, oh, the destination is 1113, it's good. And then the layer 3 pass this packet down to layer 2, But for layer 2 do not know where to send it because IP address belongs to network layer. The destination IP is 1113. But where to send this frame to the layer 2 logically? There's no destination. So the host must ask the destination. So the circumstances is like this. I have the destination IP is 1113, and I want to know her MAC address. So this is the question mark, right? So this is what ARP do. When the host have a IP address, destination IP address, and you want to know the destination MAC address, right? Because layer 3 is ready, but you want to know where to send this frame to layer 2. So you will ask ARP. That's ARP. So like this pattern, right? And this ARP packet is a broadcast. Is a broadcast because the destination MAC. Oh, this is the information. Maybe there's two more information for you, but it's the broadcast. Just remember this ARP frame request. ARP request is a broadcast frame, and the information is I have 1113. Tell me the MAC address of the 1113, and broadcast it in the network, and host B and host C will receive it, and host B find the information. The MAC address asking for is 1113. Is not me. Is not me. So host B will not respond. But for host C, she found the IP address 113 is me. So host C will reply the ARP by unicast. Reply it by a response. So the request is a broadcast. The response is a unicast. By here, host A already know the destination MAC. Know its destination MAC is .3303. So this is an ARP protocol do. For RARP is the reverse ARP, right? So the function is I know the market address, but I want to know IP. So this is the only difference. So the device send out a frame to say mark is this mark, what IP it is. So you may have question, oh, this use of reverse ARP is really strange, right? What kind of situation that I have mark, but I don't know IP? Actually, is at early age, when there is some host come join in the network, know his own market address, but he wants a IP address for layer 3 communication. So he sent a RARP to a server to require his IP address. So on this RARP server, we have the configuration of IP address to this mark. So this mark should have the IP address of .1.1.1.1. So RARP server will unicast a RARP response to this host. We'll call it this diskless workstation. So this workstation will be assigned this IP address and work in the network. So this RARP will do. Right? So this is the ARP and RARP. So the next move is how to deliver the IP packet. We already know what's IP and what IP do and what is the addressing, and then we get to know how to deliver a packet. And this picture is a host. How a host deliver a packet. We know a host is like a PC, right? The PC only need to send out the packet and receive the packet on layer 3. Logically, here we said a host deliver a unicast packet. That means logically we are sending a layer 3 packet, right? For a host, and when the upper layer protocol have data to send, that means upper layer has already encapsulated some data to layer 3, and the host will judge this destination directly connected or not. How to judge? We will judge the destination IP address network number is same with my destination number, with my network number, right? So if the number of the destination address is the same as the sending host, so the destination is on directly connected network. So this step is crucial because the next move is totally different. So when it's directly connected, for example, if the sender, if the PC or host is let's say 10.0.0.1, and the destination is 10.0.0.2. We could say the network number of these two addresses is same. So the device or the host will judge this directly connected. And then the next move is to get to know the layer 2 address. To get to know where is this destination on layer 2, right? And this move is to send a ARP to resolve the hardware address, which means the MAC address of destination host. We just learned that, right? Sending out ARP to resolve the MAC address of the destination. And after that, encapsulate the packet, the layer 3 packet, in a frame with the MAC address. Actually, we recall the encapsulation, right? After sending out the ARP, knowing the destination MAC, adding the layer 2 header, and encapsulate it in a frame and send it out. Actually, it send it to physical layer, right? This is a host to do when it's directly connected. But if it is not, if my destination is a 20.0.0.2, so network number is different. So the ARP will send to resolve the hardware address of a gateway, not the destination. So this is totally different. So just remember, if destination is directly connected, resolve the MAC address of destination. If not directly connected, resolve the MAC address of gateway, because a host send out the next moves to encapsulate the frame. The frame is a layer 2 frame, so the frame never come across a layer 3 device. So the frame need to be forward inside the layer 2 network. So that's why if the destination is not in the same layer 2 network, it will send the frame into the gateway instead of sending to destination himself. Right. Then a router. After we know a host will do the router, the only difference is here. Because the router have so many ports, so many interfaces, so the host only have one interface. So the only difference is incoming packet, which means receive the packet from the outside, from one interface, and firstly judge the destination is my IP or not, right? This is the difference with host, right? Receiving a packet, judge if it is this router's IP or not. If yes, deliver the packet to operator protocol. That means encapsulate to the operator protocol. If no, destination is not mine, it's not me. So that means you need to pass through my router. Then it's the same. It's the same with the host. Directly connected or not, and encapsulated and send it out. But only the only grass or only node add is here, right? Judge is to the router himself or just pass through the router. If router himself pass to the packet to the upper layer of the router, but if it's not, pass the packet to the forwarding engine and to judge how to send it out, right? This is the only difference between router and the host. And how a host receive an IP packet, right? A packet from outside, we just imagine host B on the picture, right? Receive the packet from outside and judge whether destination is this host. If it is de-encapsulate the packet and deliver to upper layer protocol, the difference is here. If not, the router will choose how to send it out, but the IP packet sorry, the host will choose to discard the packet directly. This is the difference. Because the host will not forward a packet due to layer 3 information. The host only judge if it's me or not. Me, deliver to upper layer, not discard. For router, me to upper layer protocol, not me, search the table, search the information, and how to judge how to send it out. So this is the difference, right? And broadcast DOM. I remember that on the last chapter we mentioned about broadcast on layer 2 on data link layer. The destination mark is full F. Remember that? Full F. So when full F happened on the layer 2 network, so it will cause a broadcast DOM. Actually, on this page, it's saying the same thing. So if we just imagine it's not on layer 2, it's on layer 3. If the PC or the host is sending out a packet with destination IP address is full 1. We already learned that full 1 means network address, full 1 means all networks broadcast. So that means this packet will be sent out not on layer 2, it's on layer 3 in packet to all the nodes on the network. So this is what we call a broadcast DOM. This is a layer 3 broadcast DOM. But imagine the situation we mentioned on layer 2, if the mark is destination mark is full F, that will cause a layer 2 broadcast DOM. So it's the layer is different, they all have broadcast DOM. The method to stop them is also different, right? And for this layer 3 broadcast DOM, usually in default, a router do not forward this kind of packet because it's easy to become a certain kind of attack. So theoretically, this address will cause broadcast DOM, but in the real case, this device will choose not to forward it. Okay. Finally, other related protocol. Other related protocol, Proxy ARP. Proxy ARP, you already know what ARP is, but when we look back to the ARP's topology, we could see ARP send out a request by broadcast, right? A broadcast is a layer 2 broadcast, and this broadcast could not go across or go through a router. That means if the PC is, for example, if host C is here, it will receive the ARP request by broadcast. But if it's here, the request will be blocked by the router. Right? We will learn that in the switch knowledge because the router will block the layer 2 broadcast naturally, right? So in order to cover this situation, so we developed this technology called Proxy ARP. So the ARP request broadcasted by here, when the router is enabled Proxy ARP function, this function will unicast, will broadcast the ARP request through the router to let host C receive this broadcast, and then also to send back the ARP response by Unicast. So that means it extends the ARP's range by over layer 3 network. So this is what Proxy ARP do. And Proxy ARP is in default, Proxy ARP is disabled on router. You need to configure that by command. ICMP. So we know on IP layer, on network layer, there are 5 protocols, right? IP, ICMP, IJMP, ARP, RARP. So ICMP is another IP layer protocol with protocol number is 1. ICMP is 1. Just now we mentioned TCP is 6, UDP is 17, but ICMP is 1. ICMP protocol is 1. And ICMP is the pin is generally will be generated by pin command when we're doing the network test, network reachability test. Right. When we want to examine whether a host, whether a destination is reachable, we use ping command, right? When we do that, the device will send out an ICMP ICO request and wait for the ICMP ICO reply, right? If it could wait for the we receive ICMP ICO reply, the reachability is good. If not receive, reachability is no good. So this is the usage of ICMP. Remember, protocol number is 1. Right. This is for IP fundamental and also very important chapter. For the key point, I will give you the key point again when we do the review, right? Because our time is pressed, so we move on to the next chapter.